Almost everything you were taught about Mars is either incomplete or wrong, and a single discovery made in the last 3 years has made that impossible to ignore. For decades, we thought we understood our closest planetary neighbor. We had the rovers, the orbiters, the soil samples analyzed by robots, the red deserts photographed 1,000,000 times. The consensus was clean. Mars is a dead world, a cold, dry, airless ruin, a finished story written in rust. That consensus is breaking, and the data pouring in from missions that most people have barely heard of has pushed the crack wide open. This is the story of what we actually know about Mars now, why it matters far more than the headlines suggest, and why almost everything you thought you knew about the red planet may need to be rewritten. Start with the Mars that lived in textbooks for the last 50 years. Cold, dry, thin atmosphere, dead. A place where nothing happens anymore. That picture was not invented from ignorance. It was built from real data, the best data available at the time. The Viking landers touched down in 1976. They were the first spacecraft to successfully operate on the Martian surface, and their soil experiments became the foundation of everything that followed. The Viking biology experiments produced results so ambiguous that scientists spent decades arguing about what they meant. The official conclusion was negative. No signs of life. The soil was chemically reactive but biologically inert. That conclusion stuck. For 30 years, Mars science operated inside a framework built on the assumption that the planet was geologically dead, biologically sterile, and hydrologically finished. Then the Mars Global Surveyor found gullies, fresh ones, on slopes that should have been stable for millions of years. Then the Mars Reconnaissance Orbiter found recurring slope lineae, dark streaks that appeared seasonally, grew during warmer months, and faded when temperatures dropped. Then MAVEN found evidence that Mars once had a magnetic field strong enough to hold an atmosphere thick enough to support liquid water on the surface. Not for 1,000,000 years, not for 10 million years. For potentially 1 billion years, one planet, two completely different stories, and the second story is the one that changes everything. Water on Mars is not a hypothesis. It is a confirmed, measured, documented fact that the entire planet is trying to hide. The Mars Reconnaissance Orbiter has been circling Mars since 2006. Its Charade radar instrument can penetrate the surface and map what lies beneath. In 2018, the European Mars Express Orbiter used its own radar to detect what appeared to be a liquid water lake buried beneath the southern polar ice cap, roughly 20 kilometers wide, sitting about 1.5 kilometers under the ice, liquid despite temperatures cold enough to freeze carbon dioxide. That detection was controversial. The temperatures at that depth, even accounting for the pressure of the ice above, should have been too cold for water to remain liquid, unless there was something dissolved in it. Perchlorate salts, which are found throughout Martian soil, dramatically lower the freezing point of water. Brine. Not clean water, cold, salty, mineral-saturated brine, but liquid nonetheless. And liquid means mobile. Mobile means active. Active means chemistry is happening. In 2023, additional radar analysis found not one but possibly multiple water bodies in the same region. The findings are still debated. The radar signature could be produced by other materials. The debate is ongoing and honest. But here is the detail that the debate obscures. Even the skeptics agree that Mars has enormous quantities of water locked into its geology. The polar ice caps alone contain enough water ice to cover the entire planet in a liquid ocean 11 meters deep, if it were melted. That water did not appear from nowhere. It was there when Mars was warmer. It went somewhere when Mars cooled. Some evaporated to space when the magnetic field collapsed. Some froze into the polar caps. Some soaked into the ground and is still there, locked in permafrost layers that may extend kilometers deep across large portions of the planet. Mars is not dry. Mars is frozen. Those are not the same thing. The Martian atmosphere today is wispy and thin. Surface pressure is less than 1% of Earth's. Standing on Mars without a suit, the pressure alone would kill you before the temperature or the radiation had a chance. But the atmosphere Mars has now is not the atmosphere Mars always had. MAVEN, the Mars Atmosphere and Volatile Evolution Mission, has been studying Martian atmospheric loss since 2014. Its findings rewrote the timeline. Mars lost most of its atmosphere not slowly over billions of years, but in a series of accelerated stripping events triggered by solar activity. When the Martian magnetic field collapsed somewhere between 4.2 and 3.7 billion years ago, the solar wind began hitting the upper atmosphere directly. Without a magnetosphere to deflect charged particles, the solar wind gradually eroded the atmosphere, molecule by molecule, over hundreds of millions of years. MAVEN measured the current rate of atmospheric loss. It then ran the numbers backward. The conclusion was that Mars had a thick enough atmosphere to sustain liquid water on its surface for a period potentially lasting from roughly 4 billion years ago to somewhere around 3 billion years ago. A billion-year window. A billion years is not a brief episode. Life on Earth established itself and diversified extensively within the first billion years of the planet's history. If Mars had liquid water on its surface for a comparable period, the question of whether life had time to emerge is not science fiction. It is a legitimate scientific hypothesis that multiple ongoing missions are designed to test. The Curiosity rover landed in Gale Crater in August 2012. It was targeting Gale specifically because orbital data suggested the crater had once held a lake, not a puddle, not a seasonal wet patch, a lake, persistent, potentially long-lived. Curiosity spent its first years confirming that hypothesis layer by layer. The sedimentary rocks at the crater floor showed the chemistry and texture of material deposited in calm, standing water. Not fast-moving catastrophic floods. Calm water. The kind that takes time to settle. The kind that suggests stable conditions over thousands or millions of years. In 2014, the mission confirmed the detection of organic molecules in the rock samples. Carbon-based compounds. The building blocks of biology as we know it. The discovery was significant. It was also carefully hedged. Organic molecules are not life. They are chemistry. They can form without biology. Meteorites deliver them constantly. But in 2019, Curiosity found something harder to explain away. Seasonal methane spikes. The background level of methane in the Martian atmosphere is essentially zero. But Curiosity's instruments kept detecting bursts, spikes that appeared, lingered, and faded. Correlated with seasons. Correlated with specific locations. Methane on Earth is almost entirely biological in origin. On Mars, it could be geological. Serpentinization, a chemical reaction between water and certain rock types, can produce methane without biology. But the spikes were seasonal. Geology does not do seasons. Biology does. The debate is unresolved. The data is real. And the instrument that could settle it, the ExoMars Trace Gas Orbiter, has been measuring Martian methane since 2018 with conflicting results that have deepened rather than resolved the controversy. In the northern hemisphere of Mars, there is a vast lowland plain called Vastitas Borealis. It sits several kilometers lower than the southern highlands. It is smooth where the south is rugged, flat where the south is cratered. For decades, the hypothesis has been that Vastitas Borealis was once an ocean. Not a hypothesis born from imagination, a hypothesis born from physics. The boundary between the northern lowlands and the southern highlands, called the dichotomy boundary, shows features consistent with ancient shorelines, terraced landforms, sedimentary deposits, patterns consistent with water standing at a consistent level for long enough to reshape the terrain. In 2024, a study using data from multiple orbiters produced the most detailed reconstruction yet of what that ancient ocean looked like. Approximately 300 million cubic kilometers of water, covering roughly 20% of the planet's surface, existing approximately 3.5 billion years ago. The researchers estimated the ocean persisted for potentially millions of years before the atmosphere thinned enough to allow it to freeze. That ocean did not vanish cleanly. It retreated. It froze. It soaked into the ground. Much of it is still there, locked in permafrost beneath the surface of the northern plains. Ground-penetrating radar from current orbiters is beginning to map those subsurface ice deposits in detail. What lies under Vastitas Borealis is not barren rock. It is the frozen remnant of a planetary ocean that may be the most significant geological feature in the inner solar system, and nobody has drilled into it yet. Nobody has taken a sample from it. Nobody has measured its chemistry directly. That ocean floor, preserved under billions of years of frozen sediment, may contain the most complete record of early Martian conditions that exists anywhere on the planet. It is also where, if life ever existed on Mars, its fossils are most likely to be found. The Perseverance rover landed in Jezero crater in February 2021. Jezero was chosen specifically because it shows clear evidence of being a former lake fed by a river delta. A delta forms where a river slows as it enters standing water and drops its sediment load. The same process that forms the Nile Delta. The same process that forms the Mississippi Delta. Jezero's delta is 3.5 billion years old. It is made of layers of rock deposited over millions of years by water carrying material from across the Martian highlands. In those layers, preserved like pages in a book, is the chemical record of Mars during its habitable period. Perseverance has been drilling cores from those layers since mid-2021. The cores are sealed in titanium tubes and cached on the Martian surface. They are not being analyzed on Mars. They are waiting. The Mars Sample Return mission, currently being redesigned due to cost and schedule challenges, is intended to retrieve those cached samples and bring them to Earth laboratories. When that happens, the analysis that can be done on those cores will exceed anything a rover instrument can accomplish by orders of magnitude. Isotope ratios measured to parts per trillion, organic molecular structures resolved at the atomic level, biosignatures searched for with instruments that fill rooms rather than fit on a rover arm. The Perseverance cores may contain the answer to whether Mars was ever inhabited. They are sitting on the surface of another planet right now, waiting for a spacecraft to come and get them. That retrieval mission has been delayed. The delay is frustrating to the scientific community in a way that rarely breaks into public coverage. Those cores represent potentially the most scientifically valuable collection of material ever gathered anywhere by any spacecraft, and they are sitting in the Martian wind while budget negotiations happen in Washington. Mars is a planet under siege by its own atmosphere. Dust storms on Mars are not like dust storms on Earth. On Earth, a major dust storm might reduce visibility to a few hundred meters. On Mars, global dust storms have been observed to reduce surface solar flux by 90%, blanketing the entire planet in a rust-colored haze for months. The 2018 global dust storm killed the Opportunity rover. Opportunity had operated for 14 years, traveling over 45 kilometers. The storm cut off its solar panels. The batteries drained. The rover never recovered. Dust storms on Mars are driven by a feedback loop. Sunlight heats suspended dust particles. The heated particles create convection. Convection lifts more dust. The storm feeds itself. The dust itself is not simply sand. Martian dust is fine, micron-scale particles coated in perchlorate compounds and iron oxides. The perchlorates are toxic to Earth biology. They are also oxidizing agents that would destroy organic molecules on the surface, which is one reason the Viking biology results were so ambiguous. The soil that Viking tested was not inert because Mars has no chemistry. It was reactive because the dust coating everything on the surface is chemically aggressive, in ways Viking was not designed to handle. Any life on Mars, if it exists, does not live on the surface. The surface of Mars is actively hostile to the kind of carbon-based chemistry life requires. But a few meters down, shielded from radiation and from the oxidizing surface, chemistry, the conditions change. The permafrost layers, the subsurface brines, the protected rock environments where temperature and chemistry are stable. These are where the search for life on Mars has shifted, away from the surface and into the geology beneath it. The United States is not the only country with plans for Mars. China landed its Zhurong rover in May 2021, making it only the second country to successfully operate a rover on the Martian surface. Zhurong operated in Utopia Planitia, one of the largest impact basins in the solar system and a region where subsurface radar suggests significant buried ice. The rover detected what appeared to be evidence of water activity more recent than expected. Polygonal terrain and layered deposits suggesting freeze-thaw cycles within the last few million years. A few million years is geologically recent. The implications for whether Mars is truly dead or merely dormant are significant. China's next Mars mission is targeted for the late 2020s and includes sample return capability. If it launches on schedule, It may return Martian samples to Earth before the joint NASA-ESA Mars sample return mission does. Two superpowers, the same planet, the same scientific questions, and a set of resources that the first country to characterize will have a significant advantage in exploiting. Subsurface water ice is not just scientifically interesting. It is rocket fuel. Split by electrolysis into hydrogen and oxygen, it becomes propellant for spacecraft and breathable air for crews. Whoever maps the Martian ice deposits in sufficient detail to plan extraction operations will control the economics of crewed Mars exploration. That mapping is happening right now from orbit. The detailed ground truth will require human presence. The race to Mars is not the theatrical spectacle the moon race was in the 1960s. It is quieter, more technical, and more consequential. The first crewed mission to Mars is not science fiction. It is a logistics and budget problem with a solution that is visible from here. The missions have mapped Mars. The orbiters have measured it. The rovers have driven across it. But no human being has ever stood on it. No one has ever looked up at a Martian sunset. The sky there turns from a pinkish tan during the day to a pale blue at dusk, the exact opposite of Earth, because Martian dust scatters light differently than earthly air. No one has ever heard the wind on Mars, though the Perseverance microphones have recorded it. A thin, high-pitched sound. The atmosphere so thin that even in a strong wind, the force is no greater than a gentle breeze on Earth. No one has stood at the rim of Valles Marineris, a canyon system that stretches 4,000 kilometers across the Martian equator, up to 7 kilometers deep in places. On Earth, the Grand Canyon is 446 kilometers long and 1.6 kilometers deep. Valles Marineris makes it look like a scratch. No one has looked up at Olympus Mons from its base, the largest volcano in the solar system. 22 kilometers high, so wide that if you stood at its center, the rim would be below the horizon. You would not know you were on a mountain. You would just be standing on a plane that gently curved upward in every direction. These are not abstract geological facts. They are places. Specific, physical, real places on a world that human beings will stand on within the lifetime of people alive today. Everything the orbiters and rovers have told us about Mars is preparation for that moment, and the picture they have built is not of a dead world. It is of a world with a violent past, a complex present, and a future that may include us. Here's the version of the Mars story that almost never makes the news. If life ever existed on Mars, it may still exist. Not on the surface, not in any form we would recognize immediately, but in the subsurface brines, in the permafrost, in the chemically protected environments beneath the oxidizing crust. Microbial life on Earth survives in conditions more extreme than anything Mars currently offers. Deep ocean hydrothermal vents, Antarctic permafrost, acidic mine drainage with pH levels close to zero, rock interiors with no light, no oxygen, and temperatures near freezing. The organisms that live in those environments are called extremophiles. They are not curiosities. They are the evidence that biology, once it starts, is almost impossible to stop completely. Mars had a billion-year habitable surface period. If life emerged during that period, it had a billion years to adapt to changing conditions. The magnetic field weakening, the atmosphere thinning, the surface drying. Each change was gradual enough that adaptation was possible. Life on Earth has survived 5 mass extinction events. It survived asteroid impacts, ice ages, and volcanic episodes that blanketed the atmosphere. If Martian life reached the same adaptive sophistication that Earth life reached in its first billion years, it is not unreasonable to ask whether it might still be there. Underground, dormant, metabolically minimal, surviving. That question is the real reason every Mars mission matters. Not the geology, not the resource mapping, not the preparation for human exploration. The detection of extant life on Mars would be the most significant scientific discovery in human history. It would reframe the question of life in the universe from an improbable accident to an inevitable consequence of chemistry in the right conditions. It would mean life is not rare. It would mean life is what planets do when they have the right ingredients for long enough. And the evidence that Mars had the right ingredients for long enough is no longer hypothesis. It is data. Measured, published, reviewed, real. The Mars we thought we knew was a convenient story, a red desert, barren and finished. useful mostly as a symbol of where humans might go next if they decided to try. That story is dying. What is replacing it is stranger, wetter, more chemically complex, and more biologically relevant than anyone who watched the Viking landers touch down in 1976 could have predicted. We built the story of a dead Mars from 6 data points, 2 Viking landers, both on the same hemisphere, both in the lowest elevation, most geologically ancient terrain available. Imagine landing a spacecraft in the Dead Sea Basin and concluding that the entire Earth is below sea level and slightly salty. That is functionally what we did with Viking. Every mission since has been correcting that picture. Each correction has made Mars stranger, not simpler. The orbiters found ancient shorelines. The rovers found lake sediments. The spectrometers found organic molecules. The radar found subsurface ice. The microphones found wind. And somewhere beneath the oxidized surface in brines that perchlorate keeps liquid at temperatures that should freeze them solid. The question that science has been building toward for 50 years is still unanswered. Is anyone still home? We do not know. We will not know until we go. And the missions being designed right now are the first ones with the instruments and the ambition to actually find out. Mars was never dead. We just convinced ourselves it was because the alternative was harder to think about clearly. Now finally, seriously, and with better tools than we have ever had before, we are thinking about it. And what we are finding is making the textbooks we grew up with look like rough drafts. Thanks for watching. See you in the next one.